Section 3.6, Variation. In this section, we're going to talk about direct, inverse, combined, and joint variation. Direct variation is something that you actually see in everyday life. An example of direct variation is if you work for an hourly wage of $10 per hour, then the pay that you get is equal to 10 times how many hours you worked. So your pay directly varies in terms of hours worked. So here's our formal definition. Y varies directly as X, or you can say Y is directly proportional to X if there exists a non-zero real number K, which we call the constant of variation, such that Y equals K times X. Example 1, solving a direct variation problem. The area of a rectangle varies directly as its length. That sentence right there is going to give us our equation. So we have A equals K times L. It's direct variation. It says varies directly, so that's why I'm using that form of Y equals KX, except I'm going to use A and L. If the area is 50 meters squared when the length is 10 meters, find the area when the length is 25. So every time we have these problems, we're going to be given two situations. In one of the situations, we're going to know all of our variables. So in this case, when the area is 50 meters squared, the length is 10 meters. In the other situation, we're only going to know everything but one variable. So here I've written out both of our situations, both of the rectangles that are being talked about here. Again, the first one we know all parts. The second one, there's one part missing that we want to find. So we're going to start the problem by taking the situation that we know everything about. So area equals 50 and length equals 10. And we're going to plug it into our equation and solve for K. Plug 50 in for area and 10 in for length and solve. Once we have our K value, we can then look at the other situation. Area equals unknown and length is 25. We can use K and L to now solve for A. So our final answer is going to be the area is 125 meters squared. Next, we have direct variation as nth power. So this is the same idea, except in this situation, the problem would state y varies directly as the nth power of x. So we would have this equation, y equals k x to the n. Next, we have inverse variation. So with inverse variation, we're going to have a fraction with k in our numerator and x in our denominator. So we could have y varies inversely as the nth power of x. So that would be y equals k over x to the n. Or if we don't have the nth power going on, then it would just be y equals k over x. So y varies inversely as x. Example 2. In a certain manufacturing process, the cost of producing a single item varies inversely as the square of the number of items produced. So that first sentence right there is going to give me my equation. So I let cost be the letter C, and number of items produced I wrote as X. The cost varies inversely, so I'm going to have K over X, because it says inversely, as the square of the number of items produced. So square is the same thing as an exponent of 2. Next, it says if 100 items are produced, each costs $2. Find the cost per item if 400 items are produced. So again, I'm given two situations. I know that 100 items cost $2 each. That's one situation that I know all the variables of. The other one, find the cost per item, so I don't know the cost per item, if 400 items are produced. So here are my two scenarios. Notice that I'm writing these all out. So out to this left side here, I've got all of my information that I just pulled from the word problem. This is a really good idea to do on your homework and tests. So now I'm ready to take 102, plug those in for my c and my x, and solve for k. Okay, so once I've got k, now I can take the 400 items and my k value, plug them back into my equation, and solve for the cost per item. So my final answer here, I get $5 per item. Next, we have what's called joint variation. So joint variation is going to be something like y varies jointly as the nth power of x and the mth power of z. So we've got another variable going on here. Example 3. The area of a triangle varies jointly as the lengths of the base and the height. So there's my equation I'm going to write out. I have the area equals k times b times h. B and h stand for base and height. Base and height didn't have any exponents on them, so I'm just going to leave them as exponents of 1. No exponents written there. Now here are the two situations I have. I have a triangle with base 10 and height of 4 has area of 20 feet squared. My other triangle going on is find the area, so I don't know area, of the triangle with base 3 feet and height 8 feet. Again, I'm writing those two situations out to the side. Okay, so let's take the first situation where we know the base height and the area, and we're going to solve for our k value. And now we can plug in our k value and base and height of our other example and solve for the area. Maybe some of you already knew that we were going to get k equals 1/2 because we know what the formula for area of a triangle is. This next example is about the vibrations of a steel guitar string. And I wanted to give you a quick idea of what a steel guitar is. You hear it in a lot of country music. So here's a little clip of it. It's a pretty cool instrument. Example 4, solving a combined variation problem. The number of vibrations per second of a steel guitar string varies directly as the square root of the tension and inversely as the length of the string. So I'm going to take this first sentence right here. I'm going to call vibrations the variable V, tensions I'm going to use T, and length L. So a couple things to focus on here. We have both direct variation and inverse variation going on. So V equals, and then it varies directly with the square root of T. So in the numerator on top, we're going to have K times square root T. And then in the denominator, since it says inversely, that's where we're going to put our L. So here's our equation. We've got direct variation going on top with K times square root T, and inverse variation going on the bottom since we are dividing by L. The two situations that we have, the first one is if the number of vibrations per second is 50, so V is 50, when the tension is 225 and the length is 0.6 meters, Find the number of vibrations per second when the tension is 196 and the length is 0.65. So here are my two situations. And now I can use the first one to solve for K. Once I've got my K value, I can take that and I can take the second situation and solve for vibrations.